Grover's algorithm. So, if you have an unordered list of size n, then classical algorithm would take around n steps to get the required item, which is means it is of order n. But Grover's algorithm uses quantum mechanics ideas and achieves the same in around root n steps. That means it is of order root n, and we'll see that one. So to summarize, Grover's algorithm in one line, what it does is it enhances the probability of the required state. So the state we are searching here will be calling it winner. So Grover's algorithm increases the probability of the winner state. So it does it in two steps. The first one is called phase inversion, and the second is called inversion about mean. So for this, discuss about the phase inversion. So suppose we have a superposition state of equal superposition state of two qubits, and we want to find the state 1 1. Then what in phase inversion step, we use an operator which we call as oracle operator, and when we act on the state, inverses the sign of the amplitude. So here we were looking for one state 1 1, and when oracle operated on the state, its sign got changed from plus to minus. So this is what oracle does. Graphically, we can see the same. All are of 1/2 state, and when oracle operator acts, the sign of the winner state is flipped from 1/2 to -1/2. But does it help anyway? So before oracle acts, the probability was around was 1/4, and even after it acts, it is 1/4. So you see, since probability is directly proportional to amplitude square, the minus sign doesn't make any difference. So though the amplitude of the winning state changed, the probability remains same. So to increase the amplitude of the required state, the next trick is inversion about mean. So to understand inversion about mean, let's look at classical example. Suppose we have four numbers x1, x2, x3, x4, and we want x3 state, and when oracle acts, it changes the sign of x3, which then it becomes -10. Then the x1, x2, x3, x4 are 10, 10, -10, and 10 respectively. And when oracle, that the same is represented graphically, where x3 sign is flipped when oracle acts. And in this figure we have represented the same numbers. We have also here phi is also represented. Here phi is the average of all the numbers x1, x2, x3, and x4, and these arrows represent nothing but how far the numbers are from the average, and the direction represents the direction from average to number. That's it. And so what we do in this step is we flip the arrow about the average. So what do I mean by that? Suppose let's take x1, x2, and x4. You have 10, and it is 5 units from the average, which is 5. 10 minus 5 is 5. We flip this arrow about average. So when we do that, we get 0. So 10, when you invert about mean, I act an operator called inversion about mean, it becomes 0. So similarly, let's take -10, which was x3. It is 15 units from the average, which is 5. So when you flip it around the average, or in simple words, rotate 180 degrees out average, it becomes 5 plus 15, which is 20. So all the numbers x1, x2, x4 got 0, and x3 became 20, which was the required state. So you see the required state amplitude increased and others got decreased. So the same idea is used in superposition, and we'll see how soon. So what happened precisely was, we'll say each number is xi, and you see how far each is from the average, which gives xi minus a. Because you want to invert, you change the sign, it becomes a minus xi. And because you want to shift, invert about mean, it's just like shifting the origin. So you add amplitude. So a plus a minus xi, you get 2a minus xi. And the same thing is done for all x1, x2, and x3, x4. Average was 5, 2a minus xi, which gives 0, 0, 20, 0 respectively. So the same idea is used for superposition, equal superposition of two qubit state, where winning state had amplitude minus 1 by 2 and others had 1 by 2. When you apply inversion amount mean, the winning state amplitude becomes 1 and rest of them become 0. So we did the same thing where average becomes was 1 by 4. So amplitude of 0, 0, 0, 1, 1, 0 is 2a minus xi, which is 0, and amplitude of winning state was 1. So when you measure the superposition state now, you always get a winning state 1 1 with probability 1, so which was required. Hence we found our required state by applying Grover's algorithm. So let's look at another example, equal superposition of 3 qubits, and here our winning state was 0, 0. Let's assume our winning state is 0 0 0, and once you apply oracle, the sign of the winning state changes. And next, when you apply inversion about mean, the amplitude of winning state becomes 5 by 2 root 8 and the of others decreases to 1 by 2 root 8. But is it enough? But still we can apply the same trick and increase the amplitude more, so that we get the 0 0 0 our winning state more number of times. That is, increase the probability of 0 0 0. So we once again apply the same trick. We once again apply the oracle, then we get the sign of the winning state changes. And when you apply inversion about mean, the amplitude of the winning state becomes 11 by 4 root 8. Now 11 by 4 root 8 whole square gives around 0.94. That means whenever you measure the superposition state now, around 94% times you get the probability, you get your winning state with a probability 0.94. So yeah, again Grover's algorithm did pretty well. Just in 2 steps you could find, you get the winning state, you get the superposition state as same as winning state which was required. So to summarize, this is the circuit, oracle to for the phase inversion, and this is sometimes called diffuser. Which this does the job of inversion about. So this is repeated around root 10 times. So now with a particular example, our previous example, we will see how to implement using quantum circuits. So we'll take the same example, superposition of 2 qubit state and winning state as 1 1. The oracle one is a pretty simple one. The unitary matrix required to flip the phase of 1 1 is this unitary matrix, and this unitary matrix is nothing but a control CZ gate which is represented by this. So the oracle is nothing but this gate, it's control Z gate. Now, so the inversion about mean, we need to figure out what is the unitary operator first. So for that, we first, let's say x is a column vector where each represents the amplitude after oracle acts 1 by 2, 1 by 2, 1 by 2, and minus 1 by 2. So generally we can write x as this matrix x1, x2, x3, x4, a column vector. So now we define a matrix called A where each element is 1 by 4, 1 by 4, 1 by 4. And when you do AX, what we observe is each element is the average of x1, x2, x3, x2 and x1, x2, x3, x4. So AX is a column vector which each element is an average. So but what we want to achieve is we want 2 times the average minus each number. So how would that be an average from? Since AX is average, 2 times average would be 2AX minus X is nothing but the column vector X. So that means that would be 2A minus I operates on X column vector. So finally we want this operator to act on our superposition state 2A minus I. So let's dig this more. So if you observe, A can be written as ket S times bra S. So where S is the equal superposition state which we talked about, and for example where n is 2, S is this, superposition state, and it is represented by this column vector. And so simply for any n, then superposition state would be 1 by n. N cross 1 column vector which each element is 1 by n. So in conclusion, we wanted to implement an operator 2a minus y, but we found that a is nothing but ket S times bra S. So we want to implement our operator 2 ket S bra S minus I. So we want gates, quantum gates, which represent this unitary matrix. So So for n equal to 2, this set of gates perform the job of this operator. So yeah, even and this can be generalized very well as this form, where first you apply all Hadamard's gates, just like this one, and then all X gates. Then here there was one CZ matrix. Here it's C as the control Z matrix, and then all X, then an Hadamard gate. So this is equivalent to 2 ket S bra S minus I operator. So this is the final circuit, the oracle operator, the CZ, and this is the inversion about mean operator. Then finally you measure and you get 1 1, the winning state. So and this is generalized circuit for any where inversion about mean operator we discussed, and the oracle operator depends on what kind of state you are searching for. So you might have noticed that I have skipped this explanation of how we got this, but to get this from first principles, what you need to do is you need to see what combination of gates would result in inversion about mean operator, which is 2 ket S minus I. But a simple example can be, but a hand wave explanation can be, first apply Hadamard gates to come out of superposition. Then since most of them are zeros, apply X. Then this control Z operator changes the sign. Then to reverse all the stuff, you can add X gates and H gates again. This is a very hand wave explanation, but yeah, figuring out from first principles is difficult. So first, let's look at geometrical interpretation of Grover's algorithm, which will have some good consequences we will discuss. So again, we'll take the same example where S is this equal to proportional state of 2 qubits and W is the 1 1 state, and this is how we can draw. If we take W winning state as y-axis and S, this will be S. Now we introduce another state called S dash state, which is 0 0 plus 0 1 plus 1 0. If you observe that this state is orthogonal or perpendicular to the winning state. So when you plot this, you get this sort of figure. So now let's write S in terms of winning state and S dash. So S will be cos theta times S dash plus sin theta times winning. And when you apply bra of W on both sides of the equation, you get this. Since W and S dash are perpendicular, this term becomes 0 and these two terms are left, and sin theta becomes W times S. Now let's expand this. So S can be generically written as 1 by root 2, and this state and the winning state can be ket of X, where X is one among these things. And note that what I mean by here is if n is 4, then it represents all superposition state, all possible combinations of 0 1. And similarly, if n is 8, then it represents these combinations. So expanding bra W and ket S, we get X this. Since X is orthogonal to all other states, they become 0, and 6 and bra X, ket X gives 1. So ultimately this is 1 by root n, and theta is sine inverse of 1 by root n. So yeah. So let's see now what happens in Grover's algorithm. So you have W and S, you have S dash. So when oracle operator acts, what oracle operator does is it reflects S about S dash, or it reflects S state about X axis. So you see this S got reflected about this, and now it became this UWS state. And the next, and if to convince you that it's reflection, you can take an example of 2 qubit state where this is S dash state and this is S and this is UWS. By symmetry, we can understand that these two should, by symmetry, S and UWS should should subtend the same angle with S dash, because there's the only difference in this sign. So this indeed is the reflection. So on acting oracle operator, you get reflection about S dash. So now what inversion about mean does is, after you have this UWS state, after acting the oracle operator, it reflects the UWS about the superposition state S. So for example, in this question, in this state, UWS got reflected about S state, and it became this state U0 UWS state. So and now this subtends an angle 3 theta with S dash. Now you see, as you continue these iterations, this U0 UW state becomes closer and closer to W state. And finally, this is what we wanted. We brought the superposition state closer to the winning state. So when we measure the superposition state, we get winning state most number of times. Now the question is, how many iterations? If you might have observed, for n equal to 2, we did only one iteration. For n equal to 3, we did only 2 iterations. And then for any n, is there any generalized answer? Now here, geometrical interpretation will help us. So after first iteration, you might have noticed that U0 UW makes an angle 3 theta with the S dash. And for second iteration, if you calculate the same, you get it's 5 theta. So by induction, for after t iterations, it should make 2t plus 1 times theta. So ultimately, what we want is S to coincide with W. For that, it should make pi by 2 minus pi by 2 with the horizontal after t iterations, because that's when S coincides with W. So here theta is the angle with the S dash state. So since after pi by 2 iterations, it's substitute 2t plus 1 times theta, which should be equal to pi by 2, as your superposition state should coincide with winning state. We if we calculate, we get t as pi by 4 by theta minus 1 by 2. Now we know that theta was sin inverse 1 by root n, which can be approximated using Taylor series as 1 by root n. Then this will be t, but t is number of iterations. It has to be something like an integer, a natural number. So when you take the floor of it, so that you get with least iterations you can achieve, it is pi by 4 root n. So if you substitute n equal to 2 or n equal to 3, you get the same number of iterations which we did last time. So that is why Grover's algorithm is around root n. And thank you. So for n equal to, so if we substitute n equal to 2, we get around which we get this floor value as 1. That's why we did only one iteration. And when if you do n equal to 3, you get this floor value as 2. That's why only 2 iterations would suffice. And this also tells that Grover's algorithm is of order root n. So thank you.